Hi, I'm Michelle Nguyen, and my drug is Pepcid, or known as famotidine. The brand name is Pepcid, the generic name is famotidine, and that is the chemical name. What the drug is used for. Pepcid, or famotidine, is an over-the-counter and prescription drug that is commonly used for the treatment of heartburn and ulcers. When you should not take the drug. If you have allergies to H2 blockers such as cimetidine, ranitidine, and nizatine, or if you have stomach cancer, chronic kidney disease 3A or 3B, or chronic kidney disease 4 or 5, significant interactions with other drugs. Famotidine is used to reduce stomach acid, so stomach acid must be present in order for the drug to work properly. Other interactions with other drugs are atazanavir, dasatinib, and dalredine. An interesting fact about the drug, it is also used for dogs to reduce stomach acid. Here, my molecular formula is C8H15N7O2S3. I am now going to show the skeletal structure of the drug. A skeletal structure is a shorthand representation of atoms and bonds in a molecule. There can be single, double, or triple bonds. In this structure, there are only single and triple bonds. The carbons are not shown but are implied by lines. Each line represents carbons on each endpoint. Hydrogen atoms are implied and are bonded to each carbon unless stated otherwise. Atoms that are not carbon and hydrogen must be specified in the structure, such as the nitrogen, sulfur, and oxygen. All the atoms want to have an octet, which means 8 valence electrons around them. And that is shown with the single and double bonds and the lone pairs. Here I'm going back in to add lone pairs to the atoms that need to satisfy their octet still, which is on the nitrogens, sulfur, and oxygens. Below, I will show the expanded structure. In the expanded structure, I will explicitly show where the carbons and hydrogens are. Here you can see me adding in the hydrogens that are bonded to the nitrogen. Now I will also go back and show where the hydrogens are bonded to the carbon. I'm now adding the hydrogens to the nitrogens. I'm also adding the nitrogen that's bonded to the carbon and the hydrogens that are bonded to the nitrogen. In this structure, I will also go back in and add the lone pairs to the atoms that need to satisfy their octet. Now I will show the molecular geometry of each central atom. The bent structure will be represented by blue, which can be 2 bonds and 1 lone pair, or 2 bonds and 2 lone pairs. Next, I'm going in and showing tetrahedral, which is 4 bonds and 1 lone pair. Next is the orange, and it is 3 bonds and 0 lone pairs, which is trigonal planar. Next is trigonal pyramidal, and that is represented by 3 bonds and 1 lone pair, and that is the purple. For this portion of the project, I will show you the molecular formula and the molar mass calculations for my drug famotidine. So the molecular formula for my drug famotidine is C8H15N7O2S3. And now I will show you the calculations for the molecular weight. So we will use the atomic weight from each element on the periodic table to calculate the molecular weight for the drug. So as we can see from the molecular formula, we have 8 carbons. So we'll go ahead and put 8, and then in the parentheses will be the atomic weight of carbon, which is 12.01 grams per mole. The next one, we have 15 hydrogens, and the atomic weight for hydrogen is 1.008 grams per mole. And then next we have 7 nitrogens, and that will be 14.01 grams per mole. And then we have 2 oxygens, which is 16.00 grams per mole. And then the last one will be 3 sulfurs, which is 32.07 grams per mole. And basically we will put that into the calculator and punch it out. It will be 337.48 grams per mole. And that will be the molecular weight for famotidine right here. And that is already rounded out to the hundredths place. I'll be showing the hydrogen bonding with water. So I'll show how this molecule can form hydrogen bonds with water. I've already drawn out the bent water molecules around the molecule, and as you can see right here, this water molecule, its hydrogen is getting donated to this nitrogen, and this hydrogen in this water molecule is also getting donated to this oxygen. So these are the hydrogen donors. Here's another one, and another one. And a hydrogen bond is when a strong electronegative atom, such as nitrogen, oxygen, or fluorine, is covalently bonded to a hydrogen atom, so such as NH, OH, or FH. So now I'm going to demonstrate the ways my molecule famotidine or Pepsid can form hydrogen bonds with water. And I've already drawn out the bent water molecules in my drug. So if I zoom in, you can see this hydrogen is getting donated to this nitrogen. And this is also a hydrogen donor, and this water molecule is donating its hydrogen to the nitrogen. This is also a donor, same thing, the hydrogen is getting donated to the nitrogen. And I've labeled all of them, so this is also a donor, 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 and donor. And now I'll explain the acceptors. This water molecule right here, the oxygen is accepting the hydrogen from this NH. And this is also an acceptor where this oxygen is accepting this hydrogen from this NH. And I've also written out all the acceptors. So this is an acceptor, this is an acceptor, and so on and so forth. So here I have my drug Pepsid and famotidine, and I've already highlighted these sections where their polar portions are. So it is all in pink, and these are polar due to the lone pairs around the central atoms. And I've predicted that my molecule will be soluble in water due to the polar portions in the molecule. And since water molecule is polar, like will dissolve like, and that's why I predicted it will be soluble in water. And when I looked it up on PubChem, it had stated that water and Pepsid is very slightly soluble in water. And what that means is it will be soluble in water, but there will be some precipitates that will form. And I guess that makes sense now that I know from PubChem, because the whole molecule is not polar. There's only some portions. So very slightly soluble would make sense because it is soluble in water, but some precipitates will form as well.
So now we'll do the solutions calculations. We're given two variables, which is 2.30 times 10 to the negative 2 molarity, and then 50.0 milliliters. And we will convert that to 0.05 liters, because in the molarity equation, it'll be moles over volume, which is moles over liters. And I'll rearrange the equation to solve for moles because of the variables we've been given. And that would be 2.30 times 10 to the negative 2 molar times 0.05 liters. After we have plugged that into the calculations, it will give us the moles. After we have the moles, we want to convert the moles to grams, and we can set that up by multiplying it by the molar weight of famotidine, which is 337.48 grams, which was found in the previous portion of the project. And now that we have converted it, it will be 0.388 grams of famotidine. And how we would prepare that solution is we would weigh out the grams of Pepsid that we need in a clean beaker and then mix it with 50.0 milliliters or 0.05 liters of deionized water to make the solution. Now in part 2, I've used the weight over volume percent equation, which equals grams of solute over milliliters of solution times 100%. And we want to rearrange that to find grams of solute because we've been given everything else. Once we rearrange that, we will end up with 0.060 grams, but we want to convert that to milligrams. And we set it up using the conversion factors and we'll end up with 60